Thank you, everyone, for coming today. We are the Center for Climate Science and Engineering at the University of Toronto, and we host monthly guest lectures. I am Daniela Boden, the CSE manager, and today we are pleased to feature Brian Beatty. So before we get started, I would like to go through the land acknowledgement. So we wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. So if you haven't been here before, we are the Center for Climate Science and Engineering, a research and education center within the Civil and Mineral Engineering Department at the University of Toronto, established in 2019. So the CSE is made up of 7 faculty members who conform the executive team and who participate together in an interdisciplinary research at the intersection of engineering and climate science. So Oy American is the center director, and she focuses on structural analysis. Marianne Hatzopoulos research focuses on transportation. Paul Kushner looks at climate dynamics. Graham Norville at health and safety processes in energy and chemical engineering. Daniel Posen looks on life cycle assessment. Karen Smith focuses on atmospheric science. Marianne Tucci focuses on building science, and then me, the CSE manager. So why we work together and what we are trying to do. So within some of the key activities going on at the CSE are education around climate science and engineering. There are 2 graduate courses that have been developed and run in UFT on top of 8 online learning models that were developed and are available for use in entire higher education environments. The team also works to do research. So the faculty members are carrying out collaborative research projects at the intersection of the climate science and engineering. And finally, the team works to do outreach events, just like this one, where we invite the public or other university people to come and give a presentation about topics that we feel are aligned with the mandate and the vision we have at the center. Please stay tuned through the CSE channels, CSE website, LinkedIn, UFT Engineering Connect, or Eventbrite. No more details for the next guest lecture events that will come again in the fall. So I would like to introduce Brian Beatty, who has come to talk about the future of geothermal energy. Brian is a senior geothermal engineer and vice president at Salos Obrian, with 50 years of experience in the groundwater and geothermal industry. Part of his recent accomplishments includes research on drilling techniques to maximize the geothermal capacity of dense urban developments. Brian is a well-known advocate of the geothermal industry in Canada, and he is a member of several subcommittees preparing the current 2022 CSA standards for geothermal energy systems. So Brian, the floor is yours. Welcome and happy to have you here. Just let me pull it up your slides now. Here we go.
There we go. Well, thanks, Daniela. I must say it's a pleasure to speak to your group today. I'm very familiar with the downtown campus, in fact, all 3 campuses, but we have designed some of the larger geothermal systems that were recently built at the downtown campus and oversaw the recent landmark installation, so I'm quite familiar with your campus. Okay, next. So I'm going to end up with the future of geothermal, but I want to start with the history of geothermal because geothermal goes back thousands and thousands of years. So to start with, there's a lot of mystery about what's the source of energy for geothermal. Well, it comes down to there's only three. It could be the ground. That means the soil and the rock in below the ground. Number two, it could be groundwater. And lastly, it could be surface water. Those are the only three. The earliest use of geothermal goes back 10,000 years or more to ancient cave dwellings. Those pioneers of that era knew how to keep warm by using geothermal. Next slide. Next. So this is a picture I took a couple of years ago in New Mexico near Los Alamos. On the left, it's a rock face about 300 feet high, straight up, and you'll see the small holes in that, and a close-up on the right. That's actually was carved out of that rock by the civilization at that time, over 5,000 years ago. And the rock it was a warm place to live in the wintertime because New Mexico is snow, and it was a cool place to live in the summer. So I consider that society the developers of geothermal energy in the world. Next slide. So I'm just going to skip through over some of the major geothermal developments in around the world in the last century. In the 1800s, 1892, the first district heating was done in Boise, Idaho. And they tapped into warm water at very shallow depths that was hot enough that they could just pipe it around the small community at that time and heat all the homes. In the early 1900s, there were power plants built in Italy using very hot water, hot enough that you could produce power. In the 1920s, first real use in Canada on a major scale was in Winnipeg, surprisingly. And that was not hot water, that was cool water. In Winnipeg, they used cool water for industry. Then in the 1930s, the first real true district energy system was in Iceland. I think everybody knows that Iceland has heats about 90% of their homes and buildings with warm water from these near surface reservoirs. 1940s, and in fact 1948 was a milestone year in the geothermal industry, and one of your own professors from U of T was the leader, Professor Frank Hooper, very well-known name in the geothermal world. He developed heat pump technology because up until that point, heat pumps were not around. Next slide. Then moving on, during the 50s and 60s, groundwater cooling was used extensively throughout Ontario and Manitoba, and that involves simply drilling a well. And then I grew up on a farm just north of Toronto. We cooled the milk, the dairy milk, in vats of cold water just by pumping it from a well, and that kept the milk cool. In Manitoba, many industries were cooled during those decades in the 1950s and 60s. Then after Professor Hooper's development of heat pumps, they went into mass production in the 70s. So that's when the heat pumps got into high gear. In the 1980s, the federal government conducted a lot of very interesting research on geothermal, along with several countries from Europe. A concept called aquifer thermal energy storage was developed right in Scarborough and in Ottawa. That very unique. That has not been put into practice since then, but very unique research that was done by the federal government at that time. Next slide. Now coming into the 90s, more activity is taking place as geothermal is growing. CSA come out with a set of standards for the design and installation of systems. That was 1992. Something happened just around that time. The development of what we call closed loops was taking place. That that involved drilling a hole deep into the ground and putting pipes down. The first pipes leaked like a sieve and were totally useless. So the researchers at that time developed polyethylene pipe. Those are fused pipes, they don't leak, and that type of piping has been used ever since. Also in Sweden, there were some of the leading countries in research. They developed testing procedures for conducting the thermal conductivity of soils. And then in the late 90s, there were in Ontario, a lot of closed loop borehole fields were installed for schools, public schools for the most part. During the 2000s, there is a huge, massive growth in closed loop systems. And that's also the time that Enwave, you may be familiar with that name, they developed the deep lake cooling system for all of the downtown Toronto towers. Next slide. This was in the early 2000s. This is a project that I designed. It was the University in Oshawa, University of Ontario, and it held the title of the second largest system in the world for about 10 years. There's about 400 boreholes under that field that you're looking at to a depth of 600 feet. Next slide. This is just to demonstrate that the downtown towers are cooled by the water in Lake Ontario, and Enwave is the contractor that does that operation. Next slide. Now, just continuing on with some of the developments in geothermal. In the 2010s, the University of Toronto installed closed loop systems at both the Scarborough and Mississauga campuses, sometime before the downtown campus. We were involved with both of those projects. In the late 2020s, the current decade, a huge growth in open loop systems. Up until that point, most of the geothermal systems were closed loop. Those were loops installed in deep boreholes. Open loop is actually a water well. So I started promoting that in just a few years ago. Right now, the CSA is upgrading or updating their standards for geothermal. There will be a major advance in the CSA standards, and that's underway as we speak. Moving forward to the 2030s, the building codes are going to be calling for zero emission buildings. That will make it much easier to heat and cool buildings with geothermal if you have tight buildings. We're developing advanced drilling technology. There will be time will come within the next 10 years when it's mandated to install geothermal systems at certain projects. And we'll see a massive growth in the district energy geothermal system. Next slide. What has stimulated the geothermal growth in the last decade or so are a number of factors here laid out, starting with in 2015, the Paris Agreement, which everybody will be familiar with. That was adopted by nearly 200 nations, of course, Canada being one of them. And then a year later, Canada developed a national climate plan. That was followed a year later after that, 2017, the Toronto Green Standard. Toronto is leading the way in Canadian cities with this kind of an approach. It's a roadmap to carbon-free buildings. Then finally, and most importantly, in 2019, U of T published their low carbon action plan. Next slide. And Ron Supporta, he to me is the champion of geothermal on the campus. He's the Chief Operating Officer for Property Service and Sustainability. And he said that climate change is one of our most important challenges. And the important thing is we have a plan. And that is absolutely true. U of T is well ahead of any other campus that I'm aware of in Canada on the move to geothermal. Next slide. So looking at U of T's action plan then, the 2030 target for greenhouse gas reductions, 37% less than the 1990 levels. That's a pretty challenging objective. Geothermal will be integrated into a district heating and cooling system, eventually, I believe, at all 3 campuses. And there will be geothermal nodes. They will become what I call a subterranean classroom for students. There will be the opportunity given here for real world research. Just think of it as another gigantic lab that's buried below the ground. Next slide. When we look at geothermal in general for any application, we always start with a feasibility study. And I just wanted to identify a few items here. You start with characterizing the resource. That means the geology. You look at the groundwater, you look at surface water, all the options that a site may have, and you have to pick. Usually it's just one of those 3, whichever one is the most optimum. All systems except surface water requires drilling. So the next step in the feasibility study would be a test hole. You have to determine the thermal properties of the ground, the rock, the soil, the overburden, the temperature of the ground, and in the case of aquifers, how much water can you get out of a well, the well yields. Next step you do is you look at the energy loads for the building, because every geothermal system is connected to a building or maybe multiple buildings. To size the geothermal system, you have to know the heating and cooling loads. Then you determine the thermal energy output of the field to see if you can match those loads, and you determine development cost, because everybody needs to know a rough idea of what's all this going to cost us. That's the last step in a feasibility study. Next slide. So now we move into, from feasibility, we move forward with the full-scale design. And as I said, you start with the building energy loads. And for geothermal, you need hourly loads. Unlike conventional systems with boilers and chillers and so on, where you may only need the hottest or coldest day of the year, geothermal, you need the energy load every hour of the year. So that's over 8,000 hours. You also look at the peak loads for each day and each week and month, and the total annual over the year. Next slide. This is a typical hourly heating and cooling load summary going across for a full 12 months. Across the bottom is the January on the left and December on the right. The blue would be the cooling load. The red would be the heating load. The lines, the individual lines with dots on them, are the peak load for each month. So all of that is required in the design of a geothermal system. And well, I'll just use this slide to mention that geothermal systems like to have balanced loads, and that means the area of the blue should match the area of the red, such as on this diagram. If it's off-centered, you have some more challenges to work with. So we always strive for a balanced load. Next slide. Continuing with the design, once we have the loads, then you look at the details of the heat pumps. Every heat pump is manufactured a little differently. They perform differently. They use different temperatures and so on. And you have to understand the operating temperatures and the flow for geothermal. The flow meaning what flow are you putting down those loops in the ground, or what flow are you pulling out of the wells? So you have to understand flow and temperature. Then we do what we call numerical modeling to determine how many holes do we need if it's closed loop, and how many wells do we need if it's open loop, or what size of surface water system do we need if it's a surface water system. And the design, you end up with laying out the actual boreholes, wells, and so on. Next slide. This is an example of the energy loads that we look at. It's a little crazy diagram here, but that's a 10-year model. The up and down each year is just the cooling and the heating period. And there's about 3 curves on there. The red one is one that is out of balance. And what happens, this is a borehole field. So what happens if you don't have a balanced load, you have too much cooling, you end up heating the ground up. So that year after year, that red curve is increasing. That means the borehole field is heating up. And we have several projects right in the downtown Toronto area where that exactly is happening. That would simply means that the system was not designed properly in the first place. So we have that problem of heating up the borehole field. The green curve at the bottom is what you should strive for. It's not heating up, it's just more or less staying steady from left to right. And that's the ideal situation for a perfectly balanced energy load. Next slide. Now, moving from design, the next step, of course, would be installation, construction of the systems. So starting with closed loops. There's no other way to install closed loops other than drilling. So you bring in massive drilling equipment. This is a slide in downtown Toronto, not on the U of T campus. That well, they're heading for about 800 feet. They drill a small diameter hole, less than 5 inches in diameter, to depths of up to, well, the maximum depth is 850 feet so far. Next slide. This is just to show that you can use a variety of drill rigs. This is one that we used to own. It's a sonic rig, very high speed drilling, specially designed for geothermal. And it's just pointing out that in retrofit situations, you can drill right up, literally almost touching the building, and you can surround the building with holes, but you can't drill under that building. Next slide. Here's an example of the foundation of a 40-story tower. So we're 3 stories below ground here, and we're installing about 300 boreholes under the building. And that has now become the common way to put geothermal systems in, closed loop systems for new structures. Always put them under the building, and this is how it's done. Next slide. This is a cutaway by a gentleman, Nicholas Demers. I'm not sure where he's from, but it's a nice cutaway view of the boreholes at Landmark. You'll recognize the university buildings. This is looking southwest, and those holes go down about 800 feet, and there's a little over 400 of them. You can see the holes in the middle of the picture. That's around the King George Circle. Next slide. This is what it looks like when you connect all those pipes, so all those boreholes. So you put a whole bunch of loops in a big field, and then you have to connect them all together with pipe. And this is where I mentioned at the outset, you use polyethylene pipe. Every joint that you see there is fused. That means it's melted together, and these are designed so there can be absolutely no leaks. And that's why we can afford to put these under buildings. Once they're installed and pressure tested, they will last more than the life of the building that's above it. It has a guaranteed lifetime of 50 years, but in reality, they will last 100 years or more. Next slide. Then all that piping is brought into the building. And this is a key integral part of what you see inside a building for a closed loop system. 2 manifolds, those 2 big pipes at the top, and all the piping coming up from the boreholes below. Each one of those pipes that comes up into the manifold will be connected probably to about 10 different boreholes. So you just multiply the number of pipes you see there. There could be 15 or so times 10, that'd be maybe 150 boreholes in this particular example. And the water in the manifold goes into the building through heat exchangers. Next slide. This is the tallest building we've ever done in Toronto. This is a Toronto Community Housing project on Dan Leckie Way. It's 40 stories tall. There were about 240 boreholes installed below the foundation. That earlier photograph was the foundation of that tower. Next slide. Here we go tallest building in the world on geothermal in Korea, Seoul, 123 floors, 720 loops below that foundation. That's not the only source of energy for that building. They draw from solar. You can see a lot of the glass on there. They also draw from a river nearby and so on. But that was by far the largest geothermal tower in the world. Next slide. Now let's move to open loop. This is the type that uses water wells instead of the closed loop boreholes that we talked about before. Next slide. Same thing, you drill water wells. The main difference between a water well drilling rig and the closed loop borehole rig is the size of the equipment. These are massive drill rigs. They drill much larger diameter holes, up to 10 inches or so in diameter. They may drill to 500 feet in solid rock, so they have to be big and powerful. So they're drilling a well. This is over in Waterloo. Next slide. As soon as we drill the well, we run a 24-hour constant pumping test. This just shows the water shooting out of that well. That's about a 400-gallon-a-minute flow. And that well produces enough water to heat and cool a complete office building. And I'll show you that next, I think. Next slide. Yeah. This is a very well-known building in Canada. It was built about 3 years ago. It's Canada's first zero-carbon building. The owner of this is very proud of what they've done there. They have a solar wall on the left. They have solar panels all over the parking lot, and they have geothermal. Next slide. Here's the supply well just outside the edge of the building. By law in Ontario, any well that's drilled has to stick above ground about half a meter. That's why it's there. The owners, this is the first year that it was used. Now it's disguised in some nice attractive shrubs and so on. Next slide. For every supply well, you have an injection well, because with open loop, you pull the water out of the aquifer with one well and you put it right back into the aquifer with an injection well. So this is the injection well. And you can see the solar panels over the parking lot in the background. That's why this building is net zero. Next slide. Another building just around the corner from that one, also in Waterloo. It's a residential complex for the University of Waterloo. It's called the Hub. This entire building, 5 towers, are heated and cooled by one single well, very high capacity well. And just to give you a comparison between the open loop and closed loop, a single well here did the job of 200 closed loop boreholes. That's why the cost of geothermal is cheaper when you use this open loop technology. It only works where you have aquifers. So it's not for everywhere, and most of Toronto does not have aquifers. So that's why U of T downtown has closed loop. Scarborough, on the other hand, sits over top of an aquifer. So that an open loop system is definitely a candidate for future systems at Scarborough, at the Scarborough campus. Next slide. And my final summary here, a few bullets on the future of geothermal, where we think it's going to go over the next number of decades. For one thing, in my 50 years of work, there's been a lot of false starts in the geothermal world. We had the Kyoto Accord, we had previous accords, and they all failed one way or the other. The Paris Agreement seems to be sticking because it's been embraced by so many countries around the world. Then when that is supported by cities like Toronto with their green standards and so on, all of that almost guarantees a tremendous future in geothermal energy in Canada and around the world. So over the next few decades, we'll see some changes. One will be the heat pumps themselves. They continually are improved in performance, and that's a key to success for geothermal. Next thing that's happening in U of T is the leading the way for this, a geothermal district energy system. They're very ambitious plans for the downtown campus for district energy. And it's well advanced in the United States, but not in no systems that I'm aware of in Canada so far. So this will be a way of the future, where you heat and cool a variety of buildings, and many buildings. Some of the campuses in the United States have up to 8,000 boreholes throughout the campus, heating 50 buildings or more. So that's what we can expect in Canada. Community geothermal systems. Mattamy Homes has started one up in Markham where they're heating a complete subdivision, probably the first subdivision in Canada to be entirely heated and cooled with geothermal. That will be a way of the future, with small subdivisions, small communities, including schools and industry and office buildings and residential buildings, all being heated by a district energy system. Agriculture holds out a tremendous opportunity for geothermal. Most farmers already use geothermal one way or the other. They all have wells. They use the wells for cooling the dairy, milk, and so on. And greenhouses are about to take off. The way we grow produce in greenhouses is an old-fashioned way. You design greenhouses to open up in the summertime. Then the plants get wilted because of the high heat, and you can't use them in the wintertime because it's too expensive to heat it. Geothermal can keep those greenhouses going year-round at a constant temperature. So that will be a huge opportunity in the future. Drilling, every closed loop and open loop system requires drilling. There have been huge advancements in drilling technology, and that will continue in the next decades. There'll be specialized rigs that are developed for deep drilling, and angle drilling and every other kind of drilling. Slide. Something that has been talked about a long time in European cities and as well as Toronto, but nothing significant has happened, but I see an opportunity coming. Use of public and municipal lands for geothermal fields. When you fly over Toronto and you see massive rights of way for subways and for power lines and parkland and all kinds of open space, all of those are candidates for geothermal fields. You don't have to put them, if you can work out a deal with the municipality, you don't have to put them on the property where you're using it. Another major advance will be the ability to monitor the performance of these systems. Up until now, in fact, very seldom are geothermal systems really monitored very well. So no one knows just how well they operate. And so that's an opportunity for students doing research on this, especially with your own systems coming online. They need to be monitored on almost an hourly basis. You need to know the temperatures coming and going from the building back to the field. You need to make sure the field is not overheating or overcooling, all that kind of thing. A huge opportunity for remote monitoring of these systems. Inspection. One of the most important aspects of geothermal is inspecting the work that's being done in the field. And there isn't enough of that going on. U of T was on top of that. Our firm actually was retained on the landmark project to provide inspection services. That's so important. It's just like inspecting any other trade, like plumbing and electrical work and so on. If you don't inspect it, it won't be installed to the proper specs. Thermal modeling is hardly done anywhere in Canada. It's done in Europe quite a bit. And that's where in advance, before you install the systems, you do some modeling to predict in advance, will this field heat up? Will if it's an open loop system, will there be a thermal plume that is created that may impact a neighbor, that kind of thing? So there's almost no thermal modeling done now of these heat plumes, but a huge opportunity to do that. And we need some bright students to focus on that kind of work. And then, of course, everybody knows, I think, over the next, there's targets for 2030, there's targets for 2050. We're going to see a complete transformation from fossil fuel to geothermal heating. And I always say, you can pump all the fossil fuels you would like out of the ground. Eventually, there'll be one last drop left. Whether that's 50 years, 200 years, or 1,000 years, it doesn't matter to me. Eventually, it will be all gone because it's not renewable. Geothermal is here forever. You just have to know how to manage it. And the nice part about geothermal, it's under every single property in the world. So if you own a house in downtown Toronto, we've drilled a single well for a 100-year-old house in downtown Toronto. They can heat and cool that house with a well in their front yard. You can retrofit commercial buildings, schools, all that kind of thing. The heat and cool is all under the building that the building is sitting on. So you don't have to transport it. You don't have to drive it anywhere. You don't have to pump it anywhere. It's right on the property itself. So that will aid in this transformation from the fossil fuel to geothermal. And that's the end of the presentation. Thank you very much, Daniela. So there may be some questions.